draw the graph of the inverse function. So geometrically, what the effect is, the graph of the inverse ends up being the reflection of the graph of the original function across the line y equals x. So let me draw that for you. I'll draw that in purple. So the main feature of y equals x is in the points that make up the line, all the first coordinates are the same as the y coordinates, right? So you should go through 0, 0, 1, 1, 2, 2, 3, 3. So this is the line y equals x. And so I've given you the graph in red of y equals f of x. We want the graph of y equals f inverse of x. So here's how you can do it. Any point that's actually on the line y equals x, if you try to reflect it, it doesn't go anywhere. Any other point, so let's look at this point. This point is very nearly negative 2, 0, isn't it? So where does negative 2, 0 get reflected? Or where does it go if you just find the inverse and flip the coordinates around? Shh, shh, shh. So negative 2, 0 would go to 0, negative 2, right? And you can actually see that at work here. Well, the problem is it's a little bit off because my coordinate system's a little bit off, but the idea is that, what do I mean by that? I mean those boxes aren't true squares. If this distance were the same as this distance for each box, then this would look like this little line segment I've drawn would be perpendicular. And so what I mean by reflecting, say, this point across the line y equals x, what I mean is you're going to go the same distance perpendicularly from the line to the point, but opposite direction. So imagine lifting this point off the page, lifting it up, out, and then it landing over here. Same distance perpendicularly from the line in purple, but opposite direction. Does that make sense? It's the same thing we did when we looked at the fact that an even function has y-axis symmetry. And that feature is if you reflect the one point of the graph across the y-axis, it will land on its mirror image on the other side. Right? If you fold the graph across the y-axis, the two halves touch. Same sort of idea. So long story short then, this point in blue here is on the graph of f inverse. And you could do that for a lot of relevant points. So this point right here, now if you just do it visually, this point right here is going to flip, just eyeballing it right about here. If I make it big enough, I'll actually hit it. And this point right here, okay, I'm just kind of going perpendicularly across, trying to get the same distance away, goes over there. And then this point is on the line y equals x, so it doesn't go anywhere. So now I'm going to sketch those points, and it should look like the graph in blue should look like the mirror image of the graph in red across the line y equals x. That's the point of all this. Oh, by the way, this point looks like it's at 0, 1, so where's the mirror image going to be? 0, 1, 1, 0. It should go right through there. I'm just kind of sketching it. So that graph in blue there, that would be y equals f inverse of x visually. So if all you have is a visual representation of your function, you can get a visual representation of the inverse by reflecting it across the line y equals x.